Okay, so let's start. Today we have lecture 6. From this lecture, we come to the second part of this subject. We call it frequency response of system. So in this lecture, we have two things to deal with. First, we will talk about one more design case as a case study to show you more about time domain analysis, time domain design, okay? The design of system based on the time specifications, such as the percentage of overshoot or the peaking time. And then we will come to the introduction of frequency response. 两件事情，第一件事情总结一下前面的内容，然后再给一个 time domain design 的一个例子，然后带大家一起看一下。第二件事情呢，就是这个进入 frequency domain， 然后给大家开始介绍 frequency domain analysis 的内容。Okay, so until now, what we have learned? So basically, or generally, we learn two topics. Firstly is modeling of the control system. Secondly, is the time domain response of the system. So the modeling of system covers so many different steps, right? Firstly, we know the differential equation of a system, right? For example, if given a mass and a spring over the mass and a damper, we can know the differential equation is such things like this. Damper is D and the spring is K. These are the constants, right? So we have a differential equation like this: dx dt squared. This is mass times acceleration, ma, right? Plus d times dx over dt. So d is a damper, is proportional to the velocity, and k times x equals to the power, right? The power force. So this is called the differential equation of a system. Based on the differential equation, we can do the Laplace transform, right? After Laplace transform, we got S domain function, right? S domain function as a system. So between the output and input, we can know there is a transfer function, right? Output over input is the transfer function of the system. It is a S domain function, right? Also a S domain function. So the transfer function connects the input and the output together, right? 传递函数把 input 和 output 联系在一起，然后在建立传递函数的时候呢，我们用到了这个 effective impedance, right? Effective impedance. So for example, resistor, impedance of resistor, impedance of capacitor, impedance of inductor, right? And in mechanical system, we also have the impedance of mass, right? Impedance of the damper, right? FVS, and the impedance of spring K, right? All we need to know to build the system model. So two types of system, electrical network and a mechanical system. Actually, there are so many different types of system, electrical, mechanical, or magnetic electrical system, or some other type of systems, or motors,马达你好多系统，不仅仅是 electric 和 mechanical， 我们有很多种不同的系统。modeling 呢也有很多种不同的方法。这里呢，我们只是就是以这个 electric 最基本的 electric mechanical system 作为 sample 作为这个研究对象来看一下这个 modeling 大概一个什么样的步骤For a complicated system, the modeling built are the same way, in same way. The only difference is the transfer function is huge. So after the modeling, we got the model of the system, right? We got the model of the system. Based on this model, M-O-D-L-E, we model of a system, we can then analyze, right? Analyze the system. So we got the analysis. And after analysis, we can get the characteristics or properties of system, such as the time domain. In time domain analysis, time domain T, okay, time domain analysis, we got some specifications, right? The rise time, the peak time, the maximum overshoot, right? And the settling time, right, of the system. So they are all the parameters of a control system in time domain, right? Because we did not learn frequency domain. Now they are all about up to now they are all about time, right? In which time it comes to the peak, in which time it has a overshoot, in which time it can have a relatively stable response. After time domain design, the next step analysis, we can do some frequency response of the system. So this part we will use about 2 to 3 lectures to talk about the frequency response of the system. Even more, it's more than 3 lectures. Actually, in frequency domain response, this is almost all part of the next half semester. Okay, so we all talk about the system in frequency domain. Okay, so this works although we do not know frequency domain analysis, we can design the system based on time domain response. So let's use an example to show how we can design a system in time domain. Okay, so we know in an airplane, if an airplane fly on the in the sky, and there are so many essential parameters or essential variables we need to control, right? We need to control the airplane to make it at the right airline, right? Sometimes we need it at a different latitude, right? That means a different higher, right? Different level of latitude, and sometimes we need to turn direction, right? For example, if we come to America, from Hong Kong to America, USA, so we need to come to the North Pole of the Earth first, and then turn right to go south, right? To go south back to the other side of the Pacific Ocean. 因为你看去美国的时候，我们先往北极那边飞，飞到北极之后呢，然后呢转弯，然后往南走，偏向美国那边就到达了太平洋的对岸。其实这样飞是最近的，因为地球是球形的嘛。这样就涉及一个问题，有的时候飞机在转弯的时候，我们需要控制它的一个角度比方说这里的这个飞机它往前飞，对不对？往前面飞，然后如果它需要右转的话，时候，那它就需要调整一下这个 bank angle 5。See here, bank angle 5它需要调整这个角度。用什么调整呢？用这个东西这个阻力板 ，OK, aileron. So you see that these two plates, these two aileron has different angle, right? Has different angle. One upward, one downward. Then the airplane, due to the force from the pressure from the air, the plane will have a bank angle to the left, to the right, right? Bank angle in this direction, right? In this direction, it will turns horizontally. And if we look from forward, we can see this picture, right? A not horizontal airplane. The bank angle now is 5. Right? So this case, we use a simplified model to talk about how we design the control system to control this angle. 我们如果一个系统的话，我们需要怎么去控制这个角度具体怎么去控制我们不管，我们不知道它这个 mechanical model 是怎么建立起来的，因为它跟太多的因素相关了。我们给它简化一下，简化出一个 second order system 来看一下这个飞机是怎么调角度的。Okay, so here we have 4 important specifications. First one, the control goal is to regulate the airplane bank angle to 0 degree. Okay, so if the bank angle after the direction change, there's a bank angle, we need to recover, right, to 0 degree to keep the airplane flat, right, to be a steady wind level and maintain the wind's level orientation in the presence of unpredictable external disturbance. Because in high speed, especially in high latitude, there will be different temperature fields when the airplane fly. Therefore, we may encounter external or unwanted air disturbance 有那种稳流气流会影响飞机，对不对？有气流的话，我们要调整这个 bank angle 让飞机保持在一个水平的一个状态。So the variable to be controlled is the bank angle phi. The control design specifications. Third one, specification. 需要什么呢 Firstly, percentage overshoot, smaller than 20 degree. Percentage overshoot here, it use PO. Actually, we can also use maximum, right? Overshoot percentage. It is they are same thing. Okay, they are same thing. The second design specification is fast response time as measured by time to peak. Therefore, this specification gives two aspects, right? Two aspects. Normally, we know. How about time domain response? It will look like this. So it should be like this, right? And firstly, so this is, oh, sorry. This is the final value we want. But before it comes to the final wanted value, right? Before the settling time, it will have a peak time here, right? Because this is the maximum overshoot, right? And before the peak, this time we call it peak time, TP. Here, it is described as time to peak, right? So we want this time as fast as possible, right? We want it to be faster. Secondly, we want the percentage overshoot. Percentage overshoot, this one. Is smaller than 20%, right? 20% of what? 20% of this, right? 20% of this. So based on these two specifications or requirements, how we design a system. Actually, we can have after selecting the key parameter, we can have the simplified model of bank angle controller like this. So phi d is the desired bank angle. Okay, phi d. We input, and then we will use the amplifier to amplify to give it a gain, okay, of the desired bank angle. This gain is used for tuning, okay, for adjustment 这个是用来调整系统的。我们可以用这个参数，一会儿可以看到，它是来调整这个系统的这个状态的，系统的这个性能的。Okay, And then the signal will come to the aileron actuator. Aileron, what is the aileron? Here, okay, these two aileron. There will be an actuator. The transfer function of the actuator is 10 over s plus 10. This is the first order system, right? This is the first order system or first order element. And then the aircraft dynamics differential equation after Laplace transform is this. So this is the transfer function of airplane dynamics. After these two steps, we got a bank angle. Okay, this is the bank angle of the airplane. Sometimes we need a bank angle. Sometimes we need to come back to zero. Right, zero is one of the possible situation. And then we need a feedback of the bank angle to the input to make it a feedback control system. Okay, this is in English maybe it is a gyrographic or gyration, right? So in Chinese we call it 陀螺仪. Okay, it can test the bank angle. So the kg is 1. That means if the bank angle is 3 degrees, then the feedback will be 3 degrees here to tell the phi d. It will be a electrical signal related to 3 degrees, okay, corresponding to 3 degrees. So that is the system modeling. And then based on this block diagram, we can simplify to get the transfer function, right? To get the transfer function. After some manipulation, okay, and simplification, here there's no need to care about the detail. Because the practical problem is very complicated. The detail is very complex. There's no need to consider. We just know this transfer function can be simplified as this one. So what is this system? What is this system? Could you give me a response? Could you answer this question? Yeah, second order system, right? This is a second order system. So at the very beginning here, this is a third order system, right? Third order system. Actually, we can simplify this system as a second order system, because for second order system, we know it better. We have a systematic design strategy, right? We know the detail of a second order system. Therefore, the prototype of a second order system given here, right? Omega n squared over s squared plus 2 zeta omega ns plus omega n squared. Second order system. So next step, what is the procedure? What will be the procedure? Next step. We know the transfer function, right? This is the second order system. So here, we know to design the system is to find K, right? Is to find an appropriate K. K value, right? Based on specifications requirement. Right? Find the K based on specification requirement. So how to find it? Firstly, you can calculate what is the relationship between K and omega n, right? Maybe we can find a function like this. So here's a procedure. Omega n equals to the function of K, right? And zeta equals to a function of K. Maybe this should be G, okay? Function of K. Then, based on the time specification, we can find omega n and zeta. Then, based on the omega n and zeta, we can find a appropriate K, right? Here is a procedure. So we can name it step. This is a step 1. This is a step 2. This is a step 3. This is the design procedure. So firstly, let's see what is omega n. Omega n equals to a function of K, right? Function of K. What it is? Could you give me a expression? 大家想一下，它这里的这个 expression 应该是一个什么样子的？ Do you understand my question? Can you understand my almost? Yeah, you are approaching almost there. Omega n. So there is a relationship between omega n and here. You can find the corresponding position. So omega n equals to what? One more step. Yes, not SRT, but SQRT, square root. Okay, so it need to be square root of 11.29 K, right? What is zeta? Zeta equals to a function of K. What is zeta? Can you find it? Give you 3 minutes to find zeta. We know here 2 zeta omega n equals to this k, right? This k. And we know omega n is here. So what will be zeta? Give you 3 minutes. If you don't know what I'm asking, you can type your question. If you know my question, okay, this is zeta, and you can simplify. Simplify， 再让它简单一些。其实比较简单，对吧？就是 2 zeta， 2 zeta omega n equals to square root of 1.92 minus 2.91 k, right? Therefore, we can have both sides square to eliminate the square root, right? Therefore, we got 4 zeta omega n z square omega n square equals to 1.92 minus 2.91 k, right? And omega n square is here, right? Therefore, we can find zeta or zeta square. Okay, here zeta square is better to show the relationship equals to 0.043 over k minus 0.065. This is zeta square. Omega zeta, right? If we want zeta, it should be what? Square root of both sides, right? Square root of both sides. This is zeta. And here I have a question. If the zeta is larger, what k will be? 也就是说 zeta 和 k 之间的关系是什么样子的 ？k 不可能等于0啊。如果 k 等于0的话，那分母变成0 ，is it possible? Not possible. Smaller, right? So we have a relationship between zeta and k. If zeta we want it to become larger, k should be smaller, right? It has a inverse or negative proportional, not a proportion, negative negative trend, right? So we want a larger zeta, k should be smaller. We want a smaller zeta, k should be larger, right? K should be larger. It is the opposite direction. And omega and k. If we want omega be larger, the k should be larger, right? If when we want omega n be smaller, then k should be smaller. Okay. So how can we determine omega n and zeta? Or how can we determine k based on omega n and zeta? Now we should look back to the specifications. These two specifications 两个所需参数，两个所需要的参数，一个是 maximum overshoot，一个是什么？一个是 peak time should be fast, peak time should be short。所以说，这里有数字的是哪一个？数字的是这个 ，right? Percentage overshoot. Here, based on the percentage overshoot, we can find what? We can find zeta, right? We can find zeta. If we know zeta, we can know k, right? If we know zeta, we can know k. If we know k, we can know omega n, right? Now we will know everything. We know k, we know the system, right? So here I want you to calculate what is zeta when percentage overshoot is 20 based on this equation. 可以算一下等于多少 ？Use your calculator. Give you 2 minutes, 1 minute to find the answer. OK， 1分钟的时间把answer 找出来。zeta 应该等于多少？0.455. Yes, you're right. Let's see. Let's verify. Let's verify with the MATLAB. Okay. So zeta equals to negative log percentage overshoot 20 over 100% over square root pi square plus log percentage overshoot square. So 0.4559. So zeta is 0.4559. Okay. So we can see between the percentage overshoot and zeta, there's such a relationship. So we want, if we want the percentage overshoot to be smaller, 如果我们想让它的这个最大超调量小一点，那它这个 damper 应该大一点还是小一点？我们想让这个 overshoot 小一点，那这个 damper 应该大一点小一点？We want percentage OS smaller. 不要看这个式子 ，OK？ Neglect this expression and think about the reality. Think about reality. Here is a control system. Think about this. Think about this figure. We want this overshoot to be smaller. Now, we want a large damper or small damper. Do you still remember? Okay, small. Why? Why? This one, right? Do you still remember this? Last lecture, we introduced, this is last lecture's notes. We introduced a second order system under different case, right? On a different case. And their first case is zero damped system. We got the time response is a cosine function, right? Cosine function. And then in the underdamped second order system, we calculate the time response is a decaying sine function, right? Decaying sine function, negative plus 1. Therefore, we got a figure like this. Oh, sorry. We got a figure like this. So now I ask that question again. We want smaller percentage overshoot. What zeta will be? Larger or smaller? Okay, what else? What else? Not here? Hello? Are you here? If you are here, if you are on the class, please type 1. Okay. If you are here, please give a response to my question. What is my question? This is my question. We want percentage overshoot to be smaller. What that should be? That should be larger or smaller. What we know is this figure. 这个 test 是要考的，我也没见有同学来问我，我以为你们都能够懂。OK， larger. Anyone else？ 这个地方很重要，你需要对这个 damping 有一个认识。damper 啊，就是造成的这个 damping ratio。damper 阻尼 damper 越大，系统的 overshoot 越小。damper 越小，系统的 overshoot 越大。damper 等于0，damper 等于0，那相当于系统没有 damper， 没有 damper 它就变成了什么？它就变成了 cosine function 了 ，right？ Cosine function overshoot is 100%, right? For cosine function, here, what we want is 1. What we really get, the maximum is 2. So the percentage overshoot is 100%, right? Extremely large. This is the largest percentage overshoot, right? If there's no damping. 如果没有阻尼的话，它的 overshoot 会特别大，超调。如果有阻尼的话呢，它就会慢慢降下来，对不对 ？damper 如果越来越大，它的 overshoot 就会越来越低。当 damper 达到1的时候 ，damping ratio 达到1的时候，还有没有 overshoot？ 没有了，对不对 ？No overshoot, right? So we can see zeta equals to 1. There's no overshoot. All right. Now let's come back here. Zeta, we got this value, and we want overshoot to be smaller, Then zeta should be larger than this value. Is it right? Right? This is what we got, right? 如果我们想让这个 overshoot 小于20%，小于等于20%，那我们要知道 delta 要大一点的 ，delta 要大到0.4559，大过它。Now can you find k? What k equals to? Can you find K? Based on this function. Can you find K? Zeta, function of K. Omega n, function of K. If we find K, if we find zeta, we can find K, right? And then we can find omega. What's K? Yes, you're right. K is 0.157. Here we use 0.16, right? Or 0.16. Same. So K should be smaller, right? We know zeta, if we want zeta be larger, K should be smaller, right? So K should be smaller than 0.157, right? So we got the design of the system, right? If we know K, we know everything here. So we know the model of the system, right?但是我请大家想一个问题啊 ，K 能够无限小吗 ？K 能够特别小吗？K 不能特别小，对不对？因为 K 如果变小的话，会带来什么影响？我们看一下这个图 ，K 啊，我们找了3条线。Percentage overshoot should be smaller than 20% here. Okay, we use this one, 20%, 20.5. If K is 0.16, here is what we obtained, right? K equals to 0.16. What the peak time should be? Can you find it in this figure? Find peak time, TP. What it equals to? 2.73, right? Second. Here is this peak time. 我们发现，当 K 等于0.16的时候 ，peak time 是2.73秒。什么意思呢？就是说，如果我们把这个 K 达到这个0.16这个数值的话，那飞机调整这个角度，它达到这个最高，当然它不是稳定下来，它达到这个最高点的这个时间是用了2.73秒。我们需要这个时间怎么样？我们需要这个时间越小越好，对不对？时间越短，调整的越快。但是呢，这个 K 呢，如果我们想让这个时间变小的话，那 K 就需要变小，对不对？K 就需要变小，K 就需要变大。你看，我们如果增大 K 变成 0.2 的话，可不可以？K 变成 0.2，response 是这个点。 K 可以 0.2 吗？Can K be 0.2? No, because the percentage overshoot is larger, right? K 是不能大于0.16的，对不对 ？K 等于0.16的时候，它的 percentage overshoot 刚好是 20%，K 只能是小于0.16，对不对 ？K 小于0.16。那我们看，如果 K 变小的话，K 变小，我们刚才分析了 zeta 就会变大，zeta 变大了之后，zeta 变大了之后会导致什么呢？会导致这个 TP 变大还是变小？If zeta becomes larger, TP will be larger, right? 大家有没有发现一个 trade-off？zeta 变大 ，K 变小，K 变小，zeta 变大，对不对？K 从0.16到0.1变小了，zeta 变大了，对不对？我们刚才在这里分析的 K 变小，zeta 变大，alright？K 变小，zeta 变大，所以说 TP，你看这里，当这个 zeta 变大之后，TP 变成了3.74，peak point 在这里，它这个 peak time 变成了3.74 second，所以 TP 变大了。所以说这里有个什么？有个 trade-off，谁和谁的 trade-off 呢？peak time percentage overshoot，它两个是 TP 如果小的话 ，percentage overshoot 就会大；TP 如果大的话，当然 percentage overshoot 可以降下来，但是呢，系统的响应就会变慢，对不对？overshoot 和 peak time，它两个 peak time 肯定是越小越好，对不对？overshoot 也是越小越好，它两个都是越小越好，right？Smaller is better。但是呢，overshoot 如果变小的话，TP 就会变大；TP 如果变小的话，overshoot 就会变大。所以说这里设计的时候就要考验你了，你选择一个什么样的 K，K 可以变得 K 在这里可以小一点，但是呢，它不能特别小，特别小了之后，这个呃 TP 就会变大，对不对？所以说这个就是飞机设计的这个关键的地方，也就是说，我们对于一个你看有这个技术封锁，像乌克兰对吧？或者是美国他们的飞机设计，波音公司对吧？Boeing 他们的这个飞机设计有很多这样的细节。你说在这里，我们并不是说 K 越小越好啊，就这一个小小的参数，我们那个合适的那个 value 在哪里呢？这需要做好多次实验，可能会摔好多个实验飞机，才能够得到这个一个合适的 K，K 有可能是0.17，有可能是0.18，对不对？因为什么？因为这个 peak time 它会影响其他的这个活动，对不对？peak time 它影响这个 bank angle 恢复的这个时间，这个时间会影响很多其他的事情，所以说这个飞机设计的这个复杂和困难就在这里。 不是说设计好了这一个就可以，因为它们互相之间是相关的，而且呢，它是一个 trade off，这个需要选择一个合适的点，那个合适的点在哪里呢？我们去问 Boeing，他们是不会告诉我们的，告诉我们他们就没有办法挣钱了，对不对？他这个是技术的秘密，这个是技术的这个封锁。那我们知道什么呢？我们现在知道 methodology，我们知道怎么去设计。这样的话呢，我们如果如果他不告诉我们，我们可以自己研究啊，不只是飞机了，其他的东西也可以啊，我们可以把它设计出来啊，用相同的方法。所以说，你看飞机也好，汽车也好，有日系、德系，对不对？呃，the cars Japanese cars German cars，他们是不一样的，对不对？它有不同的风格，这个开起来也不一样。为什么？因为他们的设计师在设计 control system 的时候，选择的这个 trade off 不一样。一个 trade off 不一样，很多个 trade off 都不一样，这个车开起来效果就不一样啊，都可以转弯，都可以加速，但是具体的 performance 或者是开起来的感受就有不同的感觉啊。一般有经验的 experienced driver，you just pick him on the car and let him drive without telling the band and he can tell what the car it is。你不告诉他，他可以根据感觉把这个车，他能够大概知道是什么牌子。所以说这个感觉就在这里，这是 control 比较有意思的一个地方。OK，let's have a break, 10 minutes break to 45. Let's continue. So above all, there are time domain response of the system. And at the beginning of this lecture, we use an example to show how we design a system based on time specification. 我们怎么根据这个时间的要求去设计一个系统？接下来我们学的是频率响应 （frequency response of system）。So there are two chapters left. One is the frequency response of system. Another is feedback control system. 一个是系统的频率响应，包括 first order、second order system， 还有一些 specification， 还有 bold plot。bold plot 非常重要。Bold plot is a vital importance here, very important. You need to sketch bold plot in exam. So this chapter, mainly from chapter 8 of this book. Okay, can you find the link? Can you find the link on Moodle? I just shared this book. You can also find it on Google. Okay, and just respect the copyright. Okay, Modern Control System by Richard C. Dorff, and Robert, right? Robert Bishop, 13th edition. You can use this book. use this book as a reference, okay, on chapter 8. So this chapter's topics mainly from this book. Okay, you can, if you find something that is not detailed, you can find back the book for more details. So chapter 5, we have 3 topics. Firstly, the concepts in frequency domain analysis. So based on Laplace transform, how can we get a Fourier transform of system? And what is the steady state response of system? So what is the magnitude or gain of system? What is the phase of the system? So what is the decibel? So for different types of factors or different elements, how can we sketch the Bode plot? For complicated system, how can we sketch the Bode plot? Based on the Bode plot, what can we know of a system? So based on the Bode plot, what kind of frequency response specifications we can know? That's what we care about. This chapter, we will use at least 3 lectures. 3 to 4 lectures。接下来3到4次都是做这个我们的 assignment 2就是画 Bode plot。在这个下星期的时候 ，next week I will give you assignment 2, so to let you sketch Bode plots. Okay, so let's start from introduction. What is the frequency response method? In a time domain response, we use a step signal, right? We know if we want to know the performance of the system, we need to use a test signal. To input to the system and see the output, right? 我们需要有一个测试信号输入这个系统 input the system transfer function, and we got the output, right? We got the output. If the test signal is a step function ut, the response will be step response, right? If the test signal is delta t, we did not mention, but even though we know there's a pulse response, right? Pulse response. So in this chapter, chapter 5, the input signal will be sine omega t. Guess what is this response? 我们第一个 step function 叫做 step response。delta function 得到的 response 叫做 pulse response。当然，我们还有 ramp function 得到的是斜坡响应 ramp response，right？ramp response。那我们如果是 sin omega t，它的 response 叫什么呢？Can you tell me? Do you have your idea? 脑筋急转弯。Hello? Hello? Can you give me an answer? What it should be? Hello? Can you hear me? Sine response. OK。我跟你说了，这是一个智力题嘛。你看啊 ，Chapter 5。OK。Here. What it should be? I told you here in chapter 5, we use sine omega t, right? You use sine omega t. So the response, we call it frequency response. Frequency response. What is frequency? Frequency is omega, right? Omega is the frequency. Okay, so let's come to the topic. 什么叫做 frequency response? Give you 1 minute to read the highlighted paragraph. So the frequency response of a system is defined as what? A what? To a what signal? What is the result? Okay, let's see. So frequency response as the steady state response of a system. Input is a sinusoidal input. Output is also a sinusoidal, right? Output signal is also sinusoidal in steady state. What is the difference between input and output? Difference is in the amplitude and phase angle. What is the amplitude? What is the phase angle? What is sinusoidal signal? Sinusoidal means sine function. Sine function. Sine function we know. It behaves like this. Right? Sine function. So for a sine function, the input we can know some specifications. What is the amplitude? We call A as the amplitude of a sine function. Okay. And for sine function, for example, A sine omega t plus phi. Okay, if the function equals to this, A is amplitude, phi is a phase angle. What is omega? Omega is a frequency. Omega is frequency. 这个是 sine function 的三要素 ，three factors of sine function. Let's see example. For example, sine function, so ct equals to 5 sine 7t plus 2. What is the amplitude? What is the amplitude? Hello? Give me an interaction. Okay, 5. What is the frequency? 7 radians per second. What is the phase? 2 radians. 2 radians. So here, I want you know another thing from the vibrations. So for the frequency is how many times per second, right? It has 2 different units. So 1 radians per second equals to what? It should be like, let's see, radians per second and hertz. Okay, if it is F hertz, then the radians per second should be 2 pi F radians per second. Okay, here is the 2 units. Here are the 2 units of frequency. 什么意思呢？就是说 hertz， 大家知道 hertz 是什么意思吗？就是说一秒钟发生多少个周期 ，right? How many cycle per second? 然后 radians per second 是 how many degree per second? One cycle, there's 2 pi degree, right? Therefore, 1 hertz is 2 pi radians per second. We can use like this. So 1 hertz is 2 pi radians per second. Okay, so this is the sine function. This is the sine function. This is the input, also is the output of the system. Let's see why. Consider a transfer function like this. 我们把这个系统的 transfer function 是这样子的。然后呢，我们知道这个 sinusoidal， 我们这个 input 把它假设为 a sin omega t， 它做 Laplace transform。OK， 我们看它的output 是什么？首先把 input 做 Laplace transform， 它等于什么呢？是不是等于这个 rs， 对不对 ？rs a omega over s square plus omega square， right? If you remember, please type 1. This one. Okay. What else? Who else remember? Okay, good. So this is the input. Okay, this is the input. This is the output. Output equals to what? Equals to input times a transfer function. Right? Times transfer function. Transfer function is like this, ms over this and the input. 我们把它两个做 multiplication， 就会得到一个这样一条式子。这条式子经过 partial expansion， 它的 partial expansion 就是这一个。partial fractional expansion 就是这一个。那我们对这个 CS 再进行 inverse Laplace transform， 就会得到 CT。Right？ 那我有一个问题 ，I have a question. When t Oh, here is the answer. Sorry, here is the answer. We got the answer here. So K1 over S plus P1， 它经过 inverse Laplace transform， 我们可以得到这条式，对不对 ？Kn over S plus Pn， 它经过 inverse Laplace transform 会得到这条式。 这一个经过 inverse Laplace transform 会得到什么呢？是不是 alpha cosine omega t，right？这一个是不是 something sin omega t，对不对？那我们看这个 ct 一共有两部分，第一部分是这个 k1 exponential negative p1t until kn exponential negative pnt。当 t 等于 infinity 的时候 ，when t comes to infinity， what this element will be 0, right? It will decays to 0. Right? Understand? Do you know why? Do you know why here? Here it is said t comes to infinity, ki exponential negative pit becomes to 0. Why? Ki exponential negative pit, t, if it is infinity, it equals to ki exponential negative infinity, right? So equals to ki exponential infinity 1 over, right? Equals to ki times 1 over infinity equals to 0。大概可以这么去理解啊。因为它是一个衰减因子，当 t 等于 infinity 的时候，这些项都会消失，它都会变成0。那最后剩下什么呢？剩下 cosine omega t sin omega t， 对不对？剩下这一个，它经过 inverse Laplace 之后，会变成一个什么呢？会变成一个 something sin omega t plus phi。OK，这里这个数学细节就不用管了，大家要记住这一条，它的 output 是这里 a t j omega sin omega t plus phi。OK，这里是什么意思呢？是这个意思。我给大家看一下。Can you see a picture here? Okay. In this picture, we have two parts. One is input. The blue one is input. 蓝色的是 input. OK. 这边是什么？红色的是什么 ？output. 红色 output. This is the spring. OK. This is a damper. What is the order of this system? This is a mass. This is a mass. Spring damper mass. So what is the order of this system? Second order, yes, second order system. So we have input here, we have output here. If the input is a sine function, 我们看会发生什么啊？Input 是 sine， output 也会是 sine function。Okay. So up to now, we can see what? We can see input is a sine function. Okay. Output is also a sine function. But here, in this animation, sine function, the period becomes shorter and shorter. 这个时候我来问大家一个问题 ：omega 在这个里面 omega 有没有变化？ Think before response. Think before response. 在这里面 input signal. Okay. Okay, we got different answer, right? Which one do you support? If you support no, press 1. If you support yes, press. If you support yes, press 1. If you support no, press 0. Yes, right? It should be yes. 为什么 ？omega 是什么 ？omega 是不是 frequency， 对不对？对 ，frequency 是不是它的 period 变化之后，它每一秒发生的这个次数就会发生变化，对不对 ？From positive to negative, you see, from positive to negative at the beginning, it is loose, right? And after a time period, it becomes dense, right? 它更加稠密了，说明什么？说明同一个时间段之内，它发生的次数变多了，所以说 period 发生了变化啊，周期发生了变化。那 omega 是不是变快了？哎，omega 是不是变快了 ？Agree? Omega becomes larger. Agree? Okay, let's see. Continue. Let's see what will happen if we change omega. Continue change omega. Now, in the following time period, I have the second question. OK， 第二个问题就是 input 和 output， 它是 in phase 吗 ？in phase 就是同向吗？它的这个 phase 是相同的吗？Hello? Yes or no? Do the input output in phase? Can you understand? Do you understand what I mean? Input 和 output 它是同向的吗？OK, two yes. What about else? 是这个意思。OK, three yes. We turn back. Wait a minute. What means in phase? OK. OK, no. OK. So what is the in phase? And out of phase? We have a signal A. Okay, we have signal A. For example, C1T is A sine omega t plus phi 1. Okay, A1 sine omega t plus phi 1. C2t equals to A2 sine omega t plus phi 2. Okay, if C1t and C2t are in phase, that means phi 1 equals to phi 2. Understand? What will happen? It will move it will move together, right? In phase. If C1t and C2t are out of phase, phi 1 do not equals to phi 2. Do you understand? Can you understand this definition? Hello, give me a response. Understand, right? 就是说，如果 phi 1等于 phi 2的时候，那它两个是同时移动的啊。这个 sin 是向上，那第二个 sin 也是向上，第一个 sin 向下，第二个 sin 也是向下，那这个就是 in phase。那如果 phi 1不等于 phi 2，就会出现这样的情况啊，两个不同时运动。OK， 我们继续看这个动画。So we come to the beginning. Does it in phase now? Does it in phase now? 现在是 in phase 吗？ Yes or no? Yeah, we got one answer. What about else? Yes, in phase, right? It moves together above, together below, right? In phase. Right? And now you will see the frequency will change, okay? As a frequency change, I want you focus on the phase focusing on the phase difference。OK， 就是说在 omega 发生变化的时候，现在 omega 已经开始变化了。omega 越来越大的时候，我们看它的 phase 有没有变化。Do they in phase now? Do they in phase now? Do they in phase now? Nope, right? 大家可以看一下是不是 in phase。你看 input the blue one， 它到达最下面，对不对？它快到最下面了。Red one， 它是在最上面，对不对？所以说现在这个 phase 它就是 different。They are out of phase. They are out of phase from each other, right? Out of phase from each other. Continue. We continue. Increase phi. Increase omega. 啊，你看这个蓝色的这个 input 越来越快。OK, omega is larger and larger. What will be the output? Output will be smaller and smaller, right? 当然，极限情况下，当这个 omega 无穷大的时候 ，output 也会变成零。但是那个不是我们研究的。Okay, now we come back here. Come back here. 我们知道 input 是什么呢 ？A sin omega t。OK， output 是什么呢？刚才的啊，我们刚才看到的是什么呢？是 A t j omega absolute value sin omega t plus phi. Phi equals to phi omega equals to t j omega, the phase angle. 这个是什么意思呢？我们可以看到，在刚才的 animation 里面，它的 input output， 它的 amplitude 一不一样 ？Yes or no? Input and output not same, right? And under different omega, the amplitude has different ratio, right? 当这个 omega 不一样的时候，它的 amplitude， 它的 ratio 也不一样。这个是由谁来决定的呢？是由这个系统的 property 来决定的。我们把 output 和 input 做一个 time domain，not frequency domain，time domain。我们做一个 ratio，OK， 做一个 ratio， 然后呢，把这个 ratio 取一个 absolute value， 它等于什么呢？等于 transfer function，然后把 transfer function 的 s 变成 j omega，OK，change s to be j omega in transfer function。absolute value 啊，我们会得到一个这样的一个这个 output。那我们如果 input 我们这里也加一个 phi 的话，加一个 phi 的话比较容易写。不加，直接这样吧。这个叫做 amplitude，OK，这个叫做 amplitude，也叫 magnitude，OK，这里叫 magnitude。这个 t 就是 magnitude response。OK，magnitude response。那我们知道 omega 是什么？What omega is? Omega is a frequency, right? Omega is frequency. So this CT over RT, we also call it magnitude frequency response. 也就是说，在不同的 frequency，它的 magnitude 是不同的 ，right？它的 magnitude ratio 是不同的啊，这个是第一个。第二个带 EEQ，我们看 phase。Can you tell me the phase of CT minus phase of RT? What it equals to? What it equals to? Phase of CT is 5. Phase of RT is 0, right? Therefore, the difference is 5, right? Difference is 5. Actually, 5 is the function of omega. Actually, phi equals to the angle of t j omega. I'll show you the detail later on. Okay, I'll show you the detail later on. And you should know we call this phi. This phi is what? Phase frequency response. Okay, let's have a break to 43. 10分钟 break，然后大家理解一下这里。 No tutorial on this Wednesday. 这个星期三没有。Okay, example. Of magnitude and phase frequency response. So we have a control system, transfer function is 1 over s plus 1. This is the transfer function. And input is a sine function, okay? Input RT is a sine function. So sine omega t, okay? Sine omega t. So I want you to tell me what is the RS? We want to know output. We want to know output CT. So first step, we need to know. So we need to know CS, right? CS equals to RS input times the transfer function TS. And the inverse Laplace of CS, we got a CT equals to something. So first step, what is RS? Give you 1 minute to tell me what is RS. We know RT. What will be RS? Perfect. How did you got omega? How can you input omega? Yes, you are right. So RS is omega over omega square plus s square, right? We normally put s in front of omega, s square plus omega square. This is the input. Transfer function 1 over s plus 1. S plus 1. And after inverse Laplace transform, we can have two parts. So the response after inverse Laplace, 这个地方不需要我们去算 ，OK？ 这个地方我直接给大家不用去算。那经过拉普拉斯变换之后，它的 output 会变成什么呢？会变成一个这样的东西，变成 omega over 1 plus omega square exponential negative t plus 1 over square root omega square plus 1 sine omega t plus, minus, a little bit longer, minus arctangent omega t. Arctangent omega, sorry. So we have some elements here. We call this as the first elements, this as the second element, and this as the third element. Okay, first element, second element, and the third element here. Okay, for the first element, when time becomes infinity, what it equals to? When time becomes infinity, what the first element equals to? Time limit to infinity. 在时间无限的时候 first is 0, right? So there's no need to consider this one. Okay, there's no need to consider this one. Second one, when so second one is a function of omega, right? So output signal, the magnitude, the amplitude is this one. Input signal, the magnitude is 1, right? So we call the ratio between output and input ratio between output magnitude over input magnitude is 1 over square root omega square plus 1 over 1, right? Input magnitude is 1. This, we call this as what? This part, what it is, give a name of second part of the circle 2. It's a magnitude frequency response. The third one is also a function of omega. We call negative arctangent omega is the phase frequency response. Okay. 这个地方概念比较新也比较多，我们必须要慢慢来。如果讲快了的话，如果我们直接到怎么计算啊，怎么带公式啊什么的，大家肯定会乱掉。所以慢慢来，这个地方不需要我们大家算，只需要给你一个 response，我们能够知道什么呢？知道这个在这个 response 里面哪一个是它的 magnitude frequency response，哪个是它的 phase frequency response。OK，magnitude frequency response, phase frequency response。看有没有什么没有讲到。OK，还有一个地方需要大家知道的 steady state response 啊，当时间 t 趋向于正无穷的时候，我们把这个系统的 response 叫做 steady state 稳态。那在刚开始的时候，它叫做什么呢？叫做顺态啊，它这个系统叫 transient state，OK，现在叫做 steady state 啊，以后我们还会提及这个概念。OK， magnitude and phase frequency response。下面给大家一个特别重要的概念 ，method to find magnitude frequency response directly from transfer function。我们还是看刚才这个例子 ，magnitude frequency response， 我们把它叫做 m omega。1/square root omega square plus 1, right? Phi omega equals to negative arctangent omega, right? Negative arctangent omega. So here is a question. Is it possible to get m omega and phi omega from transfer function？ 我们怎么从 transfer function 直接得到它的这两条式呢？如果能得到 m and phi， 我们就能够直接得到这个系统的 frequency response, right? Steady state response。我们看一下怎么去做。首先，我们知道这个，我告诉大家怎么去做哈。Transfer function 是什么呢？ 1 over s plus 1, right？ 那我们要得到从 t 到这两个，我们需要4个步骤。可能不需要4个，我们先看需要几步吧。第一步 replace s with j omega in transfer function. So we got what? T j omega equals to 1 over j omega plus 1. Okay. Replace s with j omega in transfer function. Step 2. M omega equals to absolute value Tj omega. That means equals to 1 over j omega plus 1. Equals to square root omega square plus 1 over this. Hello， 大家能够知道这里是怎么算出来的吗？ What about else? 大家知道这个复数的绝对值怎么算吗？ Absolute value of a complex number. 我想你可能不知道我在问什么。Okay, we just leave it here. We will come back later. Third step. Phi omega. Phi omega is the phase angle of Tj omega equals to negative arctangent omega. Okay, so there are 3 steps. First step, replace s with j omega in transfer function. Second step, m omega, the magnitude frequency response, is absolute value of Tj omega. Okay, and third step, phi omega is the phase angle of Tj omega. Here is the arctangent omega. So this is how we obtain the frequency response in magnitude and phase. So here, let's use this example. Okay, let's use this example to show the frequency response. There are 2 questions here, right? Find the magnitude frequency response of the system and the phase frequency response of the system. Secondly, find the time response system when input is sine omega 0t. Firstly, give you 1 minute to find the transfer function. So what is the transfer function of the system? We have one loop, right? Here is the input. Input is V1, right? Output is V2. So what is the transfer function? Ts equals to V1 over V2, V2 over V1, right? Equals to 1 over RCS, right? 这个可以从之前的lecture 可以找到，应该是 lecture 4那里。Ts is 1 over RCS plus 1. R and C are constant. R and C are constant. And then we find the magnitude frequency response. Firstly, we got Tj omega equals to 1 over RC J omega plus 1, right? JRC omega. And now we denote use omega 1 to denote RC. So it can be clear, okay? It can be clear. So 1 over J omega 1 omega plus 1, right? Now let's see magnitude response of system, what it is. Square root of omega 1 omega plus 1 1 over this. Let's see. how to calculate this. This is a complex number, right? This is a complex number. And we can calculate like this. So based on the concept m omega equals to t j omega absolute value equals to t j omega times t conjugate j omega square root. Right? 这个是定义啊，这个是定义 definition。We know j omega 1 omega plus 1 over this equals to what? J omega 1 omega plus 1. Okay, and then negative j omega 1 omega plus 1. Negative j omega 1 omega plus 1， 相等的，对不对？因为分子和分母同时乘以 negative j omega 1 omega， 我们看它等于什么呢？它等于，因为它的这个 j 在分母上面嘛，它不是很方便，我们把 j 换到分子上面去，它就是omega 1 omega square plus 1， 这个是分母，分子是什么呢？是 1 minus j omega 1 omega, right? 1 minus j omega 1 omega. Can you follow me? Here, the red one. I understand the red one. Maybe it's not. 我算一个数字，给大家理解一下。那 absolute value of 是不是大家把 complex number 给忘记了 ？Hello, if you forget complex number type 1. I will explain. 18. 我们先复习一下 complex number， 这里很重要的。 我们先复习一下 complex number。那 J 是什么 ？J 它是 imaginary unit， 对不对？也就是说 J square equals to -1。OK，J equals to square root of -1。我们先记住这一条。OK，所以说对于一个复数来讲 ，a plus jb 它的 absolute value 是什么？What is the absolute value of a plus jb? This is the real axis. This is the imaginary axis. A is here. B is here. JB is here. And A plus JB is here. So the length of this line we call it A plus JB magnitude, right? So what it equals to here? Square root A square plus B square, right? So how to get this value? We use a formula. Formula is A plus JB times A minus JB square root equals to A square plus B square square root. Right? This is the absolute value of A plus JB. Here we come. This is the revision. And here we come back. M omega is the absolute value of this one. Is the absolute value of 1 over J omega 1 omega plus 1. How to calculate? How to calculate here? You can remember this equals to omega 1 omega square plus 1 square root 1 over this square root. This is the answer. OK，其他的不用管细节了，这里记住这里就可以了。就是说什么呢？A plus JB of absolute value of A plus JB 1 over A plus JB equals to A square plus B square square root 1 over this. Okay, that's it. What is the phase? Phase omega here. I can tell you it equals to arctangent, negative arctangent omega over omega 1. Oh, sorry. Omega 1, right?哦，这里讲错了一个地方，这里应该 use omega 1 to denote 1 over RC，所以说这里的话，我们可以用这个 omega 1来这么去定义一下 ，omega over omega 1，OK，把 omega 1放在下面。一般来讲 ，first order system 我们这么去表示，那就是 omega over omega 1 square，OK。Here still omega over omega 1啊，这里改一下 ，use omega 1 to denote 1 over RC，没有为什么，只是一个习惯。Okay, so so much for today's lecture. 我们今天先讲这么多，因为我感觉再讲的话，可能效果不一定好。然后大家回去看一下这个 textbook 预习一下啊，这个读一下这个预习一下，要不然的话可能妨碍理解啊，跟不上接下来的 lecture。Okay, so now let's have a review of sorry, not here, of today's lecture. Let's have a summary. So this lecture in the frequency domain analysis, we know some concepts. The phi, right, is the in phase and out phase, right? This is the phase frequency response, right? Phase frequency response. Of system, and m phi omega m omega is magnitude frequency response of system. And also we know this is the steady state response. Of a system in frequency domain, right? So we also call it frequency response. So we compare the input output in phase and the amplitude, right? And we know we use the transfer function to determine. We use the transfer function to determine the magnitude frequency response and phase frequency response. And use a first order system as an example to show the frequency response. Right? 今天可能讲的有点快，然后效果不是很好。下一次课的时候我举一些例子给大家看一下。Okay, so much for today's lecture. Thank you for your attendance.